Hello students, good evening to all of you. I hope all of you are doing well. So today we are going to start with the second order system. Okay. If you remember yesterday we completed the steady state response part. We calculated the steady state error due to any random input. We calculated the steady state error due to disturbance. We calculated the steady state error due to different standard time domain test signals. We calculated the steady state error due to different type of the system, that is type 0, type 1 and type 2. Then we generalized the error coefficients with the type of the system. Then we have solved several numericals on that. We also started with the transient response, where I've shown you the transient response of zero order system, the transient response of the first order system. Okay, so today we are going to start with transient response analysis of second order system. Now, after completion of this transient response of second order system, we are going to do the numericals based on transient response analysis of first order and second order system. So I hope my voice is audible to all of you and the screen is visible to all of you. So shall we start, guys? And I have opened the chat box also, so if any problem comes you can reply on the chat box. Okay, Srijita, so I'm starting the class now. So transient response analysis of second order system. First of all, see here, the second order system is represented by differential equation. So this is the standard differential equation of the second order system. D square ct by dt square, where ct is the output, 2 zeta omega n dct by dt plus omega n square ct equal to k omega n square rt. So this is how the standard form of differential equation of a second order system relating the input and output is represented. Here omega n is called the natural frequency of oscillation. Zeta, this is called zeta. Zeta is called the damping ratio. Okay, so if I want, I can calculate the transfer function from this standard differential equation of second order system, right? And I told you that any physical system is represented by the differential equation. So if I solve this, if I take Laplace for this will become s square cs plus 2 zeta omega n 2 zeta omega n cs scs. Okay, because we know that the initial condition is 0 because I'm calculating the transfer function. This is omega n square cs and this is k omega n square, which is a constant, into rs. Now cs can be taken common from here, so cs by rs will become k omega n square divided by s square plus 2 zeta omega n s plus omega n square. This is how the second order transfer function is represented. Here zeta is called the damping ratio, okay, and omega n is called the natural frequency of oscillation. Now what is a damping and what is the significance of damping? Why this zeta term is included in the second order system? See guys, any second order system will have natural tendency of oscillation. Okay, any second order system will have natural tendency to oscillate. Even in the second order RLC circuit, if you remember, we get a term omega n, which is equal to 1 by under root LC. You must have read in the circuit theory, right? So what is omega n? Omega n is the natural frequency of oscillation. Okay, even in the tank circuit, including L and C, so that is also second order system. So that has also tendency to oscillate. Okay, so the current in that second order system will oscillate, okay, about the steady state value. So all the second order system, whether it is mechanical system or electrical system, okay, will have natural tendency to oscillate about the steady state. Okay, and that is why we need to damp out the oscillation, because during the transient period or during the initial stage of the response, what will happen is the second order system will oscillate, and this oscillation, if it continues, then we won't be able to get our steady state, and hence the transient analysis won't be possible. Okay, and the system would never be stable, right? So if I am doing transient analysis, means anyhow I have to make the system stable. So I need to damp out the oscillation or the vibration that is present in the system. So once I oscillate that oscillation, once I damp out or eliminate that oscillation, then definitely my response after certain period of oscillation will come to its steady state, right? So that is why we use the term zeta, because zeta is very much significant here, because that term only will represent that how much the response oscillation is getting damped out. So if zeta will increase, the damping will decrease. For zeta equal to 0, the oscillation will never damp out and the oscillation will get sustained. Means it will continue to oscillate even at the steady state or infinite time period. But if I increase the zeta and take the optimum value of zeta, then definitely all the oscillation is going to damp out. So see here, I have represented what is the significance of damping. What is the significance of damping? So if damping is absent in the system, then what will happen is, say if I am drawing or plotting the time response analysis of second order system, Ct versus T, response versus T, then what will happen is the response will increase, but it will oscillate about the steady state, and since damping is absent, that is zeta equal to 0, it will continue to oscillate for infinite time period, and I will not be able to calculate the steady state value. I will not be able to determine the steady state value. In this particular case, final value theorem will not be applicable. Okay, so I can say that if the damping is absent in the system, that is if zeta equal to 0, the response will be oscillating with its natural frequency of oscillation, that is omega n. Since there is no damping present, this will oscillate with a frequency of oscillation omega n. But if I increase the value of this damping ratio, or I can say that if damping is present, that is zeta is not equal to 0, then what will happen is the oscillation, the response will first oscillate, and since damping is present, it will decrease the magnitude or amplitude of the oscillation, and the oscillation amplitude will continue to decrease, and finally my response will come at the steady state. This is the steady state value of output or the steady state value of input. So the response after oscillation getting damped out, the response will finally reach to the steady state. So this system is finally going to be stable. Okay, and After that, we can do the stability analysis. That is how much it is stable, or if settling time is high. Hello students, welcome back. So tell me if you have if you have understood this or not. Tell me guys if you have understood this or not. Shall I move on to the next slide? Yes, Indrani, there was a certain network problem. That is why internet was not coming. Okay. Ritvik understood? Okay, let us move on to the next slide. So this is the significance of damping. That is why we use the term damping. Now see, this is how the second order system is represented, the standard second order transfer function. What is this? The standard second order transfer function. Now see, if I put the value of k, that is the system gain, as 1, then Cs by Rs will become omega n square by s square plus 2 zeta omega ns plus omega n square. And this is my closed loop transfer function, because by default we calculate the closed loop transfer function when we do the transient analysis. Now, if I ask you what is the type of the system, you cannot comment on that because this is closed loop transfer function. So convert this into a open loop transfer function. Just assume unity feedback system and apply. So for type, for determining the type, just assume unity feedback system and apply the concept numerator by denominator minus numerator. Okay, so the open loop transfer function GS will become omega n square. Okay, just apply numerator by denominator. So numerator is omega n square, it will be as it is. This is denominator minus numerator. So this will be becoming omega n square by s into s plus 2 zeta omega n. So I have got my open loop transfer function as this. So from here, just by watching the number of poles at the origin for this open loop transfer function, I can determine the type to be 1. So the type of the system is 1. Tell me the screen is visible to all of you or not? What is happening with the internet? Is the screen visible to all of you? Is the screen visible? Guys, tell me, because I can see that the screen is not visible to you, but my internet is working. I know what is happening. Acha, visible, na? Okay. So this is how we get the open loop transfer function. Okay, this is how we get the open loop transfer function. So from the open loop transfer function, I can determine the type of the system to be 1. So this is how it is represented. This is my forward path transfer function or open loop transfer function. HS is equal to 1 because I have assumed the unity feedback. This is RS and this is CS, and this is how the closed loop system will look like. Okay, so from here I can see the type of the system is 1. So this is how we determine the type of the system. Okay, for the second order system. Now see, you know that the S is represented as S equal to J omega. S equal to J omega means there is no amplifying term, there is no attenuation term, there is no amplifying factor, there is no attenuation factor here. It is just showing the plain oscillation. Okay, so this is my sustained oscillation. It will continue to oscillate. This is called sustained oscillation. Okay, now if S is equal to sigma plus J omega, that means here the sigma represent that the real term is amplifying the oscillation. So here negative sign is not there. Okay, positive sign is there. That means this real term will amplify the oscillation. So that is why the oscillation continue to increase and finally it will become unbounded. Okay, so these kind of oscillations are also not accepted. So the sustained oscillation or amplified oscillation are not accepted in second order transient response analysis. Okay, but the last one, that is S equal to minus sigma plus J omega, if the imaginary term is represented like this, then definitely this real part is negative, which means the oscillation will be attenuated at regular interval, or the amplitude of the oscillation will continue to decrease. The amplitude of the oscillation will continue to decrease. Okay, that is why it is decreasing at the continuous interval, and finally it will settle to its steady state. So this is how we represent the real and imaginary term, and that is how we plot it. Okay, so this is called attenuated oscillation. Is that fine? Okay. Now, you know that the closed loop transfer function is represented as GS by 1 plus GSHS, which is nothing but the standard second order transfer function omega n square by S square plus 2 zeta omega n S plus omega n square. This is represented as the ratio of numerator polynomial by denominator polynomial. And as you can see, this is a proper transfer function. Why it is a proper transfer function? Because the degree of denominator is 2 and the degree of numerator is 0. So definitely the degree of ds is greater than degree of ns. So this will be your characteristic polynomial, and this equal to 0 will be your characteristic equation. So my characteristic equation will be 1 plus GSHS equal to 0, which is nothing but S square plus 2 zeta omega ns plus omega n square equal to 0. Okay, so for closed loop transfer function, always remember the characteristic equation comes like 1 plus GSHS equal to 0, because we consider negative feedback by default. Okay, so this term will be represented as 0. Okay, so if I want to find out the roots for the second order system, the roots of this second order characteristic equation, okay, the roots of the second order characteristic equation will be coming like this. Okay, minus b plus minus under root b square minus 4ac by 2a. Okay, I know that if this is a square plus bs plus c equal to 0, then s will be represented as minus b plus minus under root b square minus 4ac divided by 2a. So this is how I have represented it. Okay, minus b plus minus under root b square, this is b square minus 4ac by 2a. So this will finally come as 2 and 2 will get cancelled, minus zeta omega n plus minus, we can take 4 omega n square common from here, so this will be 2 omega n. So 2 and 2 will get cancelled, and finally I'll be getting minus zeta omega n plus minus under root under root zeta under root 1 minus zeta square minus 1, right? Zeta square minus 1. So if I am taking zeta square minus 1, then this will be plus minus. And if I take 1 minus zeta square from here, okay, 1 minus zeta square, like 4 omega n square, I'll put it here, and 4 zeta square omega n square, I'll put it here. Okay, so 2 zeta will be coming as common. Okay, that is okay. But under root, since negative term will come, so for negative term we put j. Okay, so j will come. So j zeta under root, this will become 1 minus zeta square. Okay, like this, minus zeta omega n plus minus omega n under root zeta square minus 1. So if I put 1 minus zeta square, I take negative common here, so this will be 1 minus zeta square. So for the negative part, j will come, right? The imaginary term will come. So this is finally represented as minus sigma plus minus j omega d, because this term is actually damped frequency of oscillation. Because I am considering the value of zeta and this is attenuating the oscillation, so definitely a damped frequency of oscillation will come. So this total is represented as omega d, damped frequency of oscillation. So if somebody asks you what are the roots of the characteristic equation of a second order system, then the roots of the characteristic equation of second order system is minus zeta omega n plus minus zeta omega n plus minus omega n under root 1 minus zeta square. Okay, where zeta omega n is represented as attenuation factor or damping factor. Remember guys, damping ratio is different, that is zeta, okay, which is the ratio of actual damping divided by critical damping, but attenuating factor is damping factor. Okay, how much the oscillation is getting damped out, that will be represented by zeta omega n, and this term is called the damped frequency of oscillation, omega n under root 1 minus zeta square omega d. So this is very important, so just note it down, this part you note it down, and this part you note it down, and this term you should know, because sometimes they'll ask you what is the attenuation factor. They'll give you the transfer function and they'll ask you what is the attenuation factor. So you can calculate zeta, you can calculate omega n, and then do the calculation. Is that clear to all of you? Okay. So the roots of characteristic equation are this, and how I got it? How I got it? From the characteristic equation. So once you know the standard transfer function, okay, you can find out the characteristic equation, put this value equal to 0 and get the roots of the characteristic equation. Here the roots of the characteristic equation are nothing but the poles of closed loop transfer function. So here the roots of the characteristic equation are nothing but poles of closed loop transfer function. That is what? Minus zeta omega n plus minus j omega n under root 1 minus zeta square. So this formula you should remember. The roots of the characteristic equation or the poles of the closed loop transfer function. Zeta omega n is called the attenuation factor and this is called omega d. Okay, so minus sigma plus minus j omega d. So this is what you are getting as your roots. Now, how many types of damping are there? So depending on the value of zeta, the types of damping can be classified as undamped system, underdamped system, critically damped system, and overdamped system. You can see the value of zeta here. Okay, so for undamped system, zeta will be equal to 0. For underdamped system, zeta will be greater than 0 but less than 1. For critically damped system, this is the ideal case. Okay, but this is what accepted by the most of the industries for the practical control system analysis. Okay, so whenever you are doing transient analysis, basically we deal with under damped system because this is the optimum, because here only you can uh, take the optimum value of zeta. The optimum value of zeta ranges from 0.3 to 0.7. So here only you can find that. But zeta equal to 1 means what? Critically damped means exact damping is applied. Means that the damping which can kill all the oscillation. This is the damp. Here you are applying the amount of damping that will kill all the oscillations. Okay, so no oscillation will be seen. If no oscillation will be seen means what? Transient analysis will become very difficult. And overdamped system means zeta greater than 1. That means what? See, undamped system. Undamped means there would be no damping at all. Okay, that means you're not providing any kind of damping to the oscillating system. Underdamped system means you are providing the damping. Okay, you are providing the damping to the oscillating system, but that amount of damping is not sufficient to kill all the oscillation, or that damping is not sufficient to eliminate all the oscillations. And that is why some oscillation remains, as I've shown you here. As I've shown you here. Although this, see here, although I am providing the damping, that is zeta is greater than 0 but less than 1. Although I am providing the damping, but some of the oscillation will remain. Why it remains? Because the amount of damping is not sufficient to kill all the oscillations. But in the critical damping, what happens is you provide the exact damping that is required to kill all the oscillation. So from the idea, what you're doing is you're providing the ideal damping. That means you are able to provide the exact damping that is sufficient to kill all the oscillation. So that is the ideal case, right? Practically, this is not possible. And in the overdamped system, you have provided the critical damping, means you have provided the damping that can kill all the oscillation, but after then also you are providing extra amount of damping. Again, you listen it. What I'm telling is, in the overdamped system, you are providing the damping that has killed all the oscillation, but you continue to provide the damping. So if you provide the damping after then also, what happens is the response will become sluggish in nature. That is, the response will become very slow. The response will become very slow. Okay, the response will become very slow and sluggish in nature. तो एक बोलो एग्जांपल दो कोई भी एक अंडर डैम सिस्टम का. देखो, एक रियल लाइफ एग्जांपल दे रहा हूं. मान लो एक when you know when due to sudden disturbance, say due to high pressure of air, okay, or high pressure of wind, what happen is your door start swinging or window starts swinging. Okay, it does not come to the steady state, it starts swinging, but after few oscillation it comes to its normal position, right? So although oscillation is seen, but that will remain only for a short time period. Okay, so in case of underdamped oscillation, the amplitude of the body or the system will continue to decrease with time. Okay, because in under-damped system, there is continuous dissipation of energy. Okay, continuous dissipation of energy is there, and that is why the amplitude of oscillation will go on decreasing. What can be the example of critically damped system? बताओ. मान लो a high amount of wind is coming, okay, and the door or the window start swinging, but it returns to its normal position, okay, without any oscillation. मतलब swing किया, but it comes to its original position very quickly. That means it is a case of critically damped system. ठीक है? It is a case of critically damped system. And what can be the example of overdamped system? So when a high amount of pressure will come and the door or window swings and return to its position, but it is returning to its position very slowly. Okay, although no oscillation has been seen there, but it is returning to its normal position very slowly. Then it is the case of overdamped system. ठीक है? तो ऑसिलेशन एक तरीका से एक पीरियोडिक मोशन होता है, ठीक है? मतलब अंडर डैम मतलब एनी सिस्टम व्हिच ऑसिलेट्स and then come to the steady state after dissipation of its entire energy. Critically damped means the oscillations will not be seen because any swinging of the system will be coming to the original position or the steady state without any oscillation. And overdamped means the oscillations will not be seen, but the swinging of a door or window will come to its original position very slowly. So that is the example which I can give you to relate the underdamped, critically damped and overdamped system. तो underdamped मतलब एक सिस्टम ऑसिलेट करेगा, मान लो ये स्टेडी स्टेट है, assume that this is the steady state of the system, and this will oscillate and continue to dissipate energy, and finally it will settle to the steady state. How can I plot a critically damped system? For a critically damped system, exact amount of damping is provided due to which no oscillation is seen. So the response is plotted as, suppose this is my steady state value. So although my response will go to the steady state, see here also it was going to the steady state, but after steady state it was continue to oscillate about the steady state like this. But here the oscillations are killed because we have provided the exact amount of damping. So even if oscillation will be there, it will be very less, and finally it will settle to the steady state. So the response once reaches to the steady state continue to be in the steady state without any oscillation. And what can be the plot of this overdamped system? Suppose this is my steady state of output or input, and my response increases and reaches to the steady state, but it will reach to the steady state very slowly because extra amount of damping has been provided. So here also you cannot observe any oscillation over here about the steady state. Only in case of underdamped system you can observe the oscillation about the steady state, but in the critically damped system or overdamped system you cannot see the oscillation But the difference in between this critically damped and overdamped is the response is reaching to the steady state very fast and shows no oscillation at all. So the rise time is very fast, means the rise time is less, and the speed of response of the system is fast. Here also the response is reaching to the steady state, but the problem here is it is taking very large amount of time. The speed of response of the system is very slow and the rise time is very large. Okay, so the system becomes sluggish in nature. And undamped मतलब क्या? अभी तो मैंने आपको दिखाया था. Undamped मतलब it will continue to oscillate about the steady state. The response will never get settled. It will continue to oscillate about the steady state. Suppose this is my steady state. This will continue to with the same amplitude. This will be constant. And it will continue to oscillate. Okay. So this can be the plot of the undamped system. Underdamped system, critically damped system, and this is overdamped system. Is that clear to all of you? So is that clear? Indrani, Ritvik, Srijita, what is the difference between different kind of damping? How can you classify different kind of damping in the system? And what is the plot of the individual dampings? Okay. Now, let us see the example of second order system. See, any system is represented in the form of differential equation. Okay. Any system is represented in the form of differential equation. And to solve that differential equation, and to get a relationship between input and output, I need to take Laplace and consider or assume its initial condition to be 0 so that I can obtain the transfer function or the input-output relationship. Okay. So, the differential equation for PMMC, which is a second order mechanical system, is represented as Td is equal to J d square theta by dt square, where Td is the deflecting torque, theta is the oscillation. Okay, theta is the oscillation. Here theta is the output and Td is the input. So once you apply a deflecting torque, the pointer will oscillate about the steady state and finally it will settle to the steady state value, right? So this is how the differential equation is written for the second order system of PMMC. So this is deflecting torque Td equal to J moment of inertia d square theta by dt square plus B friction, okay, d theta by dt plus K spring constant K into theta. So you take Laplace both sides. So this will become TdS, this will become J s square theta s, this will become B into s theta s, and this will become K theta s, right? So theta s, which is the output, by input TdS will be 1 by Js square plus Bs plus K. This is how I got the transfer function. Now, my actual transfer function, if you see, is omega n square by s square plus 2 zeta omega ns plus omega n square. So, in the standard second order transfer function, the coefficient of s square was 1. But here the coefficient of s square is j. So, to make the highest power of s coefficient as 1, I need to divide numerator and denominator by j. Okay, what I'm saying is, see, for the transient response analysis, I basically concentrate on the characteristic equation. Characteristic equation means ds equal to 0. That means for the standard second order transfer function, how I have represented my standard second order characteristic equation? It was like s square plus 2 zeta omega ns plus omega n square equal to 0. Now, if you compare this part with this part, you can see that here the characteristic in the characteristic equation of the standard second order transfer function, the coefficient of S square or the coefficient of a higher degree of S is 1. But here in the given system, which is a PMMC, the coefficient of S square is J. So I can compare these two characteristic equation only when the coefficient of S square is 1. So I need to divide numerator and denominator by J. So this will become 1 by J, this will become S square, this will become B by J into S, this will become K by J. So as you can see, this was the standard second order transfer function, but I am not interested about the numerator part because the transient response analysis is done with the denominator or the characteristic equation. Okay, because I told you that the order of the system is responsible for determining the transient response analysis. Okay, or for the analysis of the transient response. So this is my denominator of the standard second order system, and this is the denominator or the characteristic equation of the given system. So I can compare this and this now because now it has been divided. So comparing equation 1 and 2, I am getting 2 zeta omega n is equal to B by J and omega n square, which is a constant, equal to K by J. So from here I can obtain omega n, which will be under root K by J, which is a natural frequency of oscillation. I can put it here to find out the value of zeta. So 2 zeta, this is under root K by J equal to B by J. From here I can find out the value of zeta, which is 1 by 2 B by under root K into J, where K is a spring constant, so it is a constant value. J is the inertia, which is a constant value. Okay, but B is the friction. Okay, friction coefficient of friction. So this value, okay, coefficient of friction or frictional coefficient is not constant. It will vary. Okay, so this will determine the amount of damping, because as B will vary, zeta will also vary, because this is only the variable, rest are constants. So if this will vary, zeta will also vary. So I can say that in a mechanical system or in the PMMC, which parameter will determine the damping? The frictional coefficient will determine the damping in the mechanical system. Similarly, in the electrical system, if I ask you which parameter will determine or provide the damping in the electrical system, which parameter will provide? So let us check the second order electrical system also. So I have seen the second order mechanical system. Now I am watching the second order electrical system. So second order electrical system can be RLC or just LC, right? But in the tank circuit, no damping is there. But in the RLC circuit, you can see the damping. Okay, what will happen is I have drawn this RLC circuit. Input is VI and I've taken in the Laplace form, so VIS. So when I am taking this circuit in the S domain, देखो बेसिकली ये टाइम डोमेन में जब रहता है तो ये R होता है, ये L होता है और ये C होता है, राइट? R L C, और ये होता है V0 T और ये होता है VIT, राइट? आपने नेटवर्क में पढ़ा होगा. तो अगर आपको इस एनालिसिस को सिंपलर करना है, इफ यू वांट टू मेक द एनालिसिस सिंपलर, just convert every time domain function to S domain, that is take the Laplace. Okay, so I know that the inductance in frequency domain is represented as j omega L or S into L. The capacitance in the frequency domain is represented as 1 by j omega C or 1 by SC. This V0 T will become V0 S. This VIT will become VIS. Now, as I have converted my input and output in the frequency domain, so Laplace of output by Laplace of input, considering the initial condition to be 0, initial condition for inductor and capacitor to be 0, I can find out the transfer function. Once I can find the transfer function, I can check the characteristic equation and compare it with the standard characteristic equation of a standard second order system. And this is how I can find out the value of zeta and omega n. So, क्या हो जाएगा? Just apply voltage division rule. Now this is also resistance, this is also resistance, this is also resistance. Okay, because reactance is given in ohms only. So I can consider this as resistance, this as resistance, this as resistance. So what is voltage division rule? if I want to find out this particular voltage of this particular branch, then this resistance divided by total resistance will into the input voltage will give me this part voltage. So V naught S will be 1 by SC, which is this resistance, divided by total resistance R plus SL plus 1 by SC into the input voltage. So input voltage is taken here. So I am getting now Laplace of output by Laplace of input. Now, if you simplify this, I will get 1 by, this part will become S square LC, this part will become SRC, this will become 1. Now, I have got my second order transfer function for the given electrical system, but I cannot compare it with the standard second order transfer function, because I know that for the standard second order transfer function, the characteristic equation, because I am just concerned about the characteristic equation, because I will anyhow I have to compare it with the characteristic equation only. So directly writing the characteristic equation of second order standard second order system. So this is how I write the characteristic equation for the standard second order system, and this is the characteristic equation of a given electrical system. So if I need to compare this part and this part, I have to take the coefficient of S square as 1. So I have to divide by LC in the numerator and denominator. So this will become 1 by LC, this will become S square, this will become R by L into S, and this will become 1 by LC, right? Now I can compare this and this. So 2 zeta omega n will be equal to R by L. This omega n square will be equal to 1 by LC. So check it here. 2 zeta omega n is equal to R by L, omega n square equal to 1 by LC. So omega n, natural frequency of oscillation, will become 1 by under root LC, and zeta will become, and just put it here to find out the value of zeta. So zeta in the series RLC circuit, I am getting it as R by 2 under root C by L. Okay, which is also denoted as 1 by 2 into quality factor, because quality factor for series RLC circuit is given as 1 by R under root L by C. This is how I give quality factor for the RLC circuit. So zeta I am getting as 1 by 2Q. So if you know the value of quality factor, directly put it and get this formula for the series RLC second order electrical circuit. So here C and L are energy storage element and they are constants. So just by varying the value of this R, I would be able to provide damping in the electrical system. So in the mechanical system, the frictional coefficient provides the damping, and in the electrical system, the resistance provides the damping. Okay, is it clear to all of you? So if any system is given to you, you can compare the any system, given system characteristic equation with the standard second order characteristic equation. So you must remember this particular characteristic equation always, so that you can compare with the given system and find out the value of zeta and omega n. Is that clear to all of you? Reply to me, guys. Is it clear to you? So till now, what we have seen? We have seen the differential equation and the standard second order transfer function, right? Which was k omega n square divided by S square plus 2 zeta omega n s plus omega n square. Then we have seen the significance of damping. Why zeta is used? It was not used in the first order system. So why you are using it in the second order system? So that theory I have given to you. Why I am using the damping ratio zeta, okay, to damp out the oscillation, because I know that the second order system will have natural tendency to oscillate about the steady state. So that is why I need to provide some amount of damping to damp out or to remove the vibration or the oscillation in the system. Okay. Then we have seen what is the type of the second order system. I know that second order will have order of 2, but what is the type? Type will be 1. I have also seen how to convert the second order closed loop transfer function into the open loop transfer function. So you also know the open loop transfer function for the second order system. Then we have seen how to represent the value of S, that is S equal to j omega, how to plot S equal to j omega, how to plot S equal to sigma plus j omega, how to plot S equal to minus sigma plus j omega. And we have seen that S equal to minus sigma plus j omega, which is the attenuating oscillation, is accepted for the second order system, because in that case only I can do the transient response analysis. Then we have seen the characteristic equation of the standard second order system, that is S square plus 2 zeta omega n S plus omega n square equal to 0. From there, I have found the roots of the characteristic equation, which are nothing but the poles of closed loop transfer function, and the roots came as S equal to minus zeta omega n plus minus j omega n under root 1 minus zeta square, where I've seen that zeta omega n is nothing but damping coefficient, sorry, attenuation factor or the damping factor. Zeta omega n is equal to damping factor or the attenuation factor. And omega d, which is the damped frequency of oscillation, it was omega n under root 1 minus zeta square. Okay. Then we have seen the different examples of second order system, which was a mechanical system and electrical system. So all that we have covered till now. So till now, I want to know if there is any doubt. Achha, we have also seen the types of damping, example of damping, the values of damping, the plots of different kind of damping of the system. Is that clear to all of you? So now I'm going to start the analysis of underdamped system. So since the critical damping is the ideal case, I'm not going to deal with that, because most of the industry will accept the underdamped design of control system only, okay, or underdamped design of second order system only. I'm not going to accept the overdamped system because the response is very sluggish in nature and speed of response of system is very slow, okay, because the transient time is very large, okay. So overdamped system is also not accepted. Also, undamped system, that is zeta equal to 0, is also not accepted, because there is no damp out of oscillations. The oscillation are sustained over there, and that is why it will never reach to the steady state. So I won't be able to find out the settling time or any kind of performance specification parameter. So I cannot do the performance analysis from the undamped system. So underdamped system is the most accepted one. Okay. So see, just like in the first order system, if you remember, I have found the response CT, okay, which was nothing but K into 1 minus e to the power minus T by tau ut. This was the response of first order system, if you remember, where tau was the time constant, K was the steady state value of output, small t was the variation in the time, and how the response is varying with time, CT was giving it to you. Okay, so this was the response. So here also I have to find out the response of second order underdamped system. Response of second order underdamped system. So for the first order system, my transfer function, standard transfer function, was K by 1 plus tau s. This was the standard transfer function for the first order system, right? So this I have shown you for the first order system. This was the standard transfer function, K by 1 tau s, and CT was K1 minus e to the minus T by tau. This was the response. So I already know the transfer function of standard second order system, right? So now I will try to find out the response. So CS by RS is omega n square by S square plus 2 zeta omega s plus omega n square. So RS will go over here. Now what is RS? I want to find out the unit step response. I want to find out the unit step response of a second order underdamped system. What I'm doing is I want to here also this response was nothing but unit step response of first order system, and this is the unit step response of second order underdamped system. So Cs will be equal to omega n square by this into 1 by s. Now I will take partial. So I hope there is no need to explain the partial, how I have taken partial. Okay, this is 1 by s because you have to take, okay, you have to do some manipulation here. So 1 by s minus this part I am writing it as s plus zeta omega n whole square. So this will come as s square plus zeta square omega n square plus 2 zeta omega ns. So this and this are already available, but zeta square omega n square is not available. So I'll do minus zeta square omega n square. Okay. Also, this part was not there. So I'll do plus omega n square. So what I am getting it here is 1 by s minus this part minus this part. Okay. So derivation is not at all important. If you want, I can derive it. Okay. In your if you want, but derivation is not necessary. Okay, but still you can see how it is derived. Okay, so Cs equal to 1 by s, this part, and here I have taken see this part I can take common omega n square 1 minus zeta square. Okay, so I know that omega n square 1 minus zeta square is omega d square. Okay, so this part I am taking it as s plus zeta omega n whole square plus omega d square. Okay, now zeta by under root 1 minus zeta square. So finally, when I'll take inverse Laplace, Ct will become 1 minus e to the power minus zeta omega n t cos omega dt minus zeta by under root 1 minus zeta square e to the power minus zeta omega n t sin omega dt. And this will become 1 minus e to the power minus zeta omega n t by under root 1 minus zeta square zeta sin omega dt plus under root 1 minus zeta square cos omega dt. So this is of the form a sin omega t plus b cos omega t. So I know that this is written as r sin omega t plus phi. R sin omega t plus phi. So Ct will finally be written as 1 minus e to the minus zeta omega n t by under root 1 minus zeta square sin omega dt plus phi. So this is the response. Which response? Unit step response of what? Second order underdamped system. Okay, this is the unit step response of a second order underdamped system, and you need to remember this expression. Just like for the first order system, I have remembered the expression, okay, because it is required in the numerical and the standard transfer function of the first order system. Similarly, for the second order underdamped system, I need to know about the standard second order transfer function and the unit step response of a second order underdamped system. So here omega d is the damped frequency of oscillation, which is omega n under root 1 minus zeta square. Phi is the representing the location of the pole in the complex plane, LHS of complex plane. Okay, so phi is given as tan inverse under root 1 minus zeta square by zeta, because here phi represents tan inverse b by a. So b by a. What is b here? B was under root 1 minus zeta square. What was a here? This one. So under root 1 minus zeta square by zeta, you can find out phi. So phi is, tan phi is this part by this part. Okay, you can also calculate cos of phi. Cos of phi will be base by hypotenuse. So zeta by 1. Okay, so cos phi is equal to zeta means what? Phi you can calculate as cos inverse zeta. So either you can use this formula to calculate the value of phi, or you can use this formula to calculate the value of phi. So remember this particular expression. Remember how to calculate this phi, and that's it. Tell me if there is any doubt. Tell me if any doubt is there. Only these two are required, guys. Okay, the derivation part is not required, but still if you want, you can check in your gate form workbook or in any standard book like IG Nagarath. Okay, whatever book you are having, you can check the derivation will be there. If you cannot understand derivation, tell me, I'll explain you again tomorrow. But derivation is not required for GATE or any MCQ exams. Okay. Is that clear? So as I was telling you, what is the phi? Phi is nothing but the angle subtended by the pole in the LHS plane with respect to negative real axis or the LHS plane. Okay. So this phi, suppose this is a underdamped system is given to you. Underdamped system is given to you. Underdamped system, from the underdamped system, I can understand that zeta will be in between 0 to 1, right? In between 0 to 1. Suppose zeta I am giving you 0.5. Zeta equal to 0.5 means what? Cos phi is equal to zeta. So cos phi is equal to 0.5. So phi equal to cos inverse 0.5, that will be 60 degree, right? So phi equal to 60 degree. Phi equal to 60 degree means what? From the, with respect to this negative real axis, this is my negative real axis. So with respect to this negative real axis, phi will make an angle of 60 degree. Phi will make an angle of 60 degree with respect to negative real axis. So with respect to negative real axis, phi will make an angle of 60 degree, and the pole will be located in the LHS of complex plane. Okay, LHS of complex plane. This part is LHS. This entire part is LHS of the complex plane. Okay. So as you can see, phi is the angle subtended by the pole. Okay, phi is the angle that is subtended by the pole or pole location. So phi is the angle subtended by the pole location in the LHS plane with respect to what? With respect to negative real axis. And I know that whenever the poles are located in the LHS complex plane, it will always occur in conjugate pair. Even if you remember, the roots of the characteristic equation were coming like S equal to minus sigma plus j omega d. Okay, that is minus zeta omega n plus minus under root j omega n under root 1 minus zeta square. So plus minus was coming or not. So that represents that second order system will be having two poles in the LHS plane, and it will be in the complex plane because minus a plus minus jb is there, right? Minus a plus minus jb is there. That means the poles will always lie in the LHS plane. And if the poles are lying in the LHS complex plane, the pole will always occur in the conjugate pair. Okay, the pole will always occur in the form of conjugate pairs. Okay. So let us understand what are pole location and their corresponding response for different kind of damping. So I have to understand pole's location and its corresponding response for different type of damping. So for that, I need to write the characteristic equation of a standard second order system. So standard second order system was written as S equal to minus zeta omega n plus minus j omega n under root 1 minus zeta square. That is minus sigma plus j omega plus minus j omega d. Right? And I know that the roots of the characteristic equation will be giving me the poles of closed loop transfer function. So the roots of this will give me the poles of closed loop transfer function. So say I am considering the first type of damping, that is undamped system. Undamped system means what? Zeta will be equal to 0. If zeta is equal to 0, this part will vanish. This entire part will vanish. That is, the attenuation part will not be there. You will be left with just plus minus j omega d. Okay, S equal to plus minus j omega d. Acha. omega d is omega n under root 1 minus zeta square. But zeta is equal to 0. No damping is there. That means omega d will be converted to omega n only, because this part will be just 1. So omega d will be equal to omega n. So S is equal to plus minus j omega n. Okay. Plus minus j omega n means what? The poles are located exactly on the imaginary axis in the form of conjugate pair. The poles are located on the imaginary axis. So poles are purely imaginary. So what was the topic? I have to determine the pole location and its corresponding response. So I know that if I am able to write the standard second order characteristic equation, that will give me the pole location, okay, or the poles of closed loop transfer function. So here the poles of the closed loop transfer function are purely imaginary, or the location of the poles are purely imaginary, because zeta is equal to 0. And from here, if you put zeta equal to 0, you are getting plus minus j omega n. Now you know that if the value of S does not include any attenuating term or amplifying term, that is the real part, okay, that means the oscillations will be sustained oscillation. They will neither decrease or increase. The oscillation will be steady oscillation or the sustained oscillation. So it will continue to oscillate even at steady state. Okay, so this is the plot of the response. This is the time domain or time response analysis plot. Okay, so this is for underdamped system. That is when zeta equal to 0, poles are purely imaginary, and the plot will look like this. Now, for the underdamped system, you know that zeta will vary in between 0 to 1. Now, this is my standard second order characteristic equation. Okay, so I'll write this. Now you put zeta any value. Suppose you take zeta equal to 0.5. Okay, 0.5 comes in between 0 to 1. So, and take omega n as 10. So take zeta as 0.5, omega n as 10. Any constant I've taken. Omega n, radian per second. So now zeta is 0.5, omega n is 10, and this is j 10 under root 1 minus 0.5 square is 0.25. So this part will become 5. So minus sigma plus minus j, and this part will come something that is called omega d. Okay. So as you can see, along with the oscillation, I have zeta omega n present. Zeta omega n is the attenuation factor or the damping factor which will try to attenuate the oscillation. So any oscillation about the steady state will be getting decreased and will damp out. And finally, my response will reach to the steady state. Finally, my response will reach to the steady state. Okay. Now, if you want to check the pole location, you can see that it is having negative real part and means it is having real part also and complex part also. Okay, imaginary part also. So it will lie in the complex plane. As you know that S equal to minus A plus minus JB lies in the complex plane in the LHS part. So the poles are in the LHS part of the complex plane. So the poles are complex conjugate. So whenever underdamped system is there, that is zeta varies in between 0 to 1. Okay, so you can take any value, zeta 0.5, 0.7, 0.3. Okay, so when you put this in the standard second order characteristic equation, you will get S as the complex conjugate part, that is minus A plus minus JB. Okay, so minus A is nothing but zeta omega n and plus JB is J omega D. So omega D is omega n under root 1 minus zeta square and minus J omega D. Minus J omega D is minus J omega n under root 1 minus zeta square. So pole location are complex conjugate in the LHS plane. And the response, as you can see, for this particular part, this was exactly the case of a second order underdamped system where the oscillations were getting damped out and finally my response reaches to the or settle to the steady state value. Okay, so since my unit step input is taken, so here steady state output is 1 or the steady state input is 1. Now next case is critically damped system. So for critically damped system, zeta is exactly equal to 1. So put it in the value of the characteristic equation, roots of the characteristic equation. So minus zeta omega n plus minus j omega n under root 1 minus zeta square. Put the value of zeta equal to 1. So this will be minus omega n, and this will be, if you put zeta equal to 1, this part will vanish. This part will become 0. So the imaginary part does not exist here. So for critical damping, the imaginary part does not exist, and that is why no oscillation will exist. Neither damp frequency of oscillation nor the natural frequency of oscillation. So this part will not remain, only the real part will remain. So minus omega n will remain. So since the order of the system is 2, okay, because I am dealing with the second order system, okay, and checking the pole location. So minus omega n plus 0, minus omega n minus 0. So two roots are there, minus omega n and minus omega n. So if somebody asks you what is the location of pole, location of the pole are real and equal, because it is lying exactly on the negative half of the real axis. Negative real axis. It is lying exactly on the negative real axis, and they are equal also. So the pole location is not only real but equal also. And for the critically damped system, I have already shown you the response plot that the system response increase and finally gets settled to the steady state without any oscillation. For the underdamped system, when the response was reaching to the steady state, it was having a natural tendency to oscillate about the steady state. But here, no oscillation is seen and it settles to the steady state and remains at the steady state. What is the reason for that? Because we have provided the damping which is sufficient to kill all the oscillation. You have provided the exact damping to the system which has killed all the oscillation. So this is how the response has been seen. So this is my pole location and this is my corresponding response. The last part is the overdamped system. Overdamped system means zeta will be greater than 1. Zeta greater than 1 means the roots of the characteristic equation first you write, minus zeta omega n plus minus j omega n under root 1 minus zeta square. This is how the roots of the characteristic equation or the poles of the closed loop transfer function looks like. Okay. Now you put zeta greater than 1, any value you put, say zeta equal to 1.5 you put. So this will be, and omega n equal to 10. So this will be minus 1.5 into 10, that is minus 15, plus minus j omega n under root 1 minus 1.5 whole square. So this part will come as negative. So if negative will come, so again a j term will come. So j into j will become j square. J square means this will become negative. So plus minus into minus. So plus part will become minus, minus part will become plus. So plus part will become minus, minus part will become plus. Okay, and this part will become, because since negative is taken outside, this part will become zeta square minus 1. Okay, again I'm explaining. You take any value of zeta which is greater than 1, and omega n you can take any value that is 10. Then when you put the value, this part will come negative. Negative part when you take outside, this part will become zeta square minus 1, and the negative part when it come outside, it gets multiplied with j. Okay, so j into j will become j square. J square is minus 1. So this plus minus will become minus plus. So I'm getting two roots of the characteristic equation or the two poles of the second order closed loop transfer function as minus zeta omega n minus plus omega n under root zeta square minus 1 and minus zeta omega n plus omega n under root zeta square minus 1. As you can see, the roots, if you check the roots of the characteristic equation, you can see that no j term is there. That means no oscillation is there. If no oscillation is there, that means the response nature is slow and sluggish. Okay. All overdamped means what? that you have already provided the damping that was enough to kill all the oscillation, but still you are providing the damping to the system. So that extra damping will make the system very sluggish, and the response will although increase and settle to the steady state, but it will be very slow, and the rise time will be very high. Okay, and the settling time will also be very high. So here if you see, the location of the poles are real only, क्योंकि ये कुछ ऐसा आएगा माइनस से ये कितना था 1.5 बोला था, ये 10 बोला था, -15 और ये मान लो आ गया 10. दिस पार्ट से आई एम अज्यूमिंग एज 12 और 10 जो भी है. So -15 -12 is -27 and -15 plus 12 is -3. So all the part is coming negative only. So one pole is say -3 and one pole is say -27. So the poles are real, negative, but unequal. So the poles are real and distinct. I can say that for an overdamped system, the location of the poles are real and distinct. Distinct means unequal. Okay, but they are lying in the LHS plane only. So for all kind of damping, for all the types of damping, whether it be undamped, underdamped, critically damped, or overdamped, the poles are lying in the LHS plane only. The poles are lying in the LHS plane only. Whether it be purely imaginary, complex, or real, they are lying in the LHS side. None of the poles are lying in the RHS. Okay, because if the pole will lie in the RHS, it will become unstable, and if it becomes unstable, no transient analysis can be done, because stability analysis is done by assuming that the system may be stable. Okay. Is that clear to all of you? Tell me, till now, if you have any doubt, you can ask me. Reply, guys. Indrani has replied. Is there any doubt? Till now? Understood. Ritvik. Okay. So let us move ahead and see, because only 2 topics are left here, and then we'll do the numerical part. So see here, characteristics of underdamped system. So characteristic of underdamped system, here we are watching 2-pole variation only, because we are dealing with the second order underdamped system. So definitely 2-pole variation only we'll see. Okay. Now, if you see here, suppose initially zeta is, say you are increasing the value of zeta. What you are doing? You are increasing the value of zeta and check the variation of pole location. This is what you are doing here. So you are increasing the value of zeta and checking the variation of the pole location along with that. So first, when zeta will be equal to 0, where the poles will lie? The poles will lie on the imaginary axis. So when zeta is equal to 0, as you have seen here, when zeta was equal to 0, the poles were purely imaginary. So the poles are purely imaginary for zeta equal to 0. So what was the value? S was equal to plus j omega n, S was equal to minus j omega n. Okay? Now, again, you increase the value of zeta. From here, from zeta equal to 0, you increase the value of zeta. So when you increase the value of zeta to say 0.2 or 0.5 or 0.7, you come under the case of underdamped system. For the underdamped system, the poles were lying on the LHS complex plane like this. And what was the real part? The real part was, because you know that for a second order system, for second order underdamped system, the roots of the characteristic equation, which are nothing but poles of the closed loop transfer function, is written as minus zeta omega n plus minus j omega d, right? So this is minus zeta omega n, real part, and this is plus j omega d. What is omega d? Damped frequency of oscillation, which is omega n under root 1 minus zeta square. And this is also minus j omega d, minus j omega n under root 1 minus zeta square. So you have got the pole lying from imaginary to the LHS complex plane. Now again you increase the value of zeta and make it equal to 1. Now once the value of zeta becomes 1, it becomes critically damped system. What do you mean by critically damped system? Critically damped system means the poles will lie on the real axis and it will be real and equal. The poles will be real and equal. And if you remember, when you put the value of zeta to be 1, then for critically damped system, zeta equal to 1, it was minus omega n and minus omega n. So real and equal. So the pole will come like this and it will lie here, minus omega n and minus omega n for the zeta equal to 1. And this is for zeta equal to 0.5. This is for zeta equal to 0. So from j omega n, it is coming to here, that is minus zeta omega n plus minus j omega d. From here it is coming to minus omega n. So this part is actually minus omega n. This part is minus omega n, here to here. Okay. Now when you increase the value of zeta above 1, it becomes overdamped. Overdamped means the poles will be on the real axis only, because no oscillation is there, so no imaginary term will be there. So poles are real only, but they are real and unequal, that is real and distinct. So the pole will lie here. One pole will lie here and the other pole will say lie here. Okay. One will be very less and other will be very large. Okay. So poles are real and distinct or real and unequal for zeta greater than 1. Say zeta equal to 1.5. Okay. So I hope you have understood it. So once I have got all the pole location, I can join them to get my root locus. So once you join the pole location, I am getting a closed semicircular path. So this is what I am getting. Closed semicircular path. So in the characteristic of underdamped system, you have seen that when the zeta will increase and the pole location will vary, then it will make a semicircular path where this distance is omega n, zeta omega n, and this distance is omega n. So definitely zeta omega n for underdamped system, it was 0.5, so minus 0.5 omega n is less than omega n. Okay, so I can see that the locus of the roots of the second order system gives a semicircle of radius omega n, because this is my radius and this radius is omega n. Okay, because although it is negative, but radius is written in positive units now, because it represents distance and distance are always positive. Okay. Now, for underdamped system, there is an angle which is subtended by the pole. Okay. For underdamped system, you have already seen that. Okay. That there is an angle which is subtended by the pole location. Okay. With respect to negative real axis. So phi also I have represented. And what is the value of phi? Either you can find it with cos inverse zeta, or you can find it with tan inverse under root 1 minus zeta square by zeta. Now, if I am asking you to find the time constant of a second order system, then you just have to concentrate on the real part. Okay. So 1 by real part, okay, magnitude of the real part. See, I have included a modulus also. So you don't have to worry about negative or positive sign, because time constant will always be a positive value. Okay. So 1 by modulus of real part will give me the time constant. So here, for the second order system, you can see that the real part was minus zeta omega n. So 1 by modulus of minus zeta omega n will be 1 by zeta omega n. So my time constant of the second order system is coming as t equal to 1 by zeta omega n. So once you know the value of zeta and omega n, you can find out the time constant of second order system. And from the pole location, you can check that the locus of the roots of semicircle will be, the locus of roots of second order system will be a semicircle, right? And underdamped system is the most accepted type of damping in the industries, where you can take the optimum value of damping in between 0.3 to 0.7. This is the range of damping ratio in which most of the linear control system will work. So the overall design and analysis of second order control system is in between the value of zeta ranging from 0.3 to 0.7. Okay. So these are the characteristics of underdamped system. Now the last part of this particular concept is performance specification parameter of underdamped system. Okay, performance specification parameter of second order underdamped system. Okay. Now what are the performance specification parameter? So these are the specifications which will give me the performance analysis of a second order underdamped system. Okay. So the first part is the delay time. Okay. Delay time means what is the time taken by the response to reach to the 50% of the steady state value of output. Okay. What is the time taken by the response of the second order system to reach to the second 50% of the steady state value of the output. Okay. And the formula for that is TD is equal to, तो मतलब ये फर्स्ट अटेम्प्ट में ही पहुंच जाता है. ठीक है. डिले टाइम मतलब क्या कि कितना टाइम लग रहा है एक सिस्टम रिस्पॉन्स को टू रीच टू द 50% of the steady state value of output at the first attempt, and this is represented as TD equal to 1 plus 0.7 zeta by omega n. 1 plus 0.7 zeta by omega n. So once you know the value of this TD, you can also represent your CT, that is your output response, okay, unit step response of a second order underdamped system, as 1 minus e to the minus zeta omega n TD by under root 1 minus zeta square sine of omega t. लिखते हो, यहां पर भी देखो t लिखते थे, राइट? यहां भी क्या लिखते थे? स्मॉल t. I am just explaining you how I got this formula, although it is not required, but still I am explaining so that you won't be confused. So in the expression of CT, this is my expression of CT. Okay. This is how I express the unit step response of a second order underdamped system. Now, if you want to find the value of delay time Td, I know that it is the time at which the response will reach to the 50%, that is 0.5 of the steady state value of output. What is the steady state value of output? Since you are taking unit step input, and I know that at steady state, my at steady state, the value of the steady state output and the steady state input is same, so it is equal to 1. So 0.5 into 1 at this. So this is happening, this particular part is happening at which time? This is happening at time Td. So in place of small t, you have to write capital Td. And phi value, you know that it is tan inverse under root 1 minus zeta square by zeta. So when you put all that value and try to find out the value of this Td, that is delay time, it will come as 1 plus 0.7 zeta by omega n. Please remember, see, please note here that this is omega n, not omega d. Okay. Okay. Now, what is rise time? Rise time is actually the time taken by the response of an underdamped system to reach to 100% of the steady state value. Again, steady state value of output or input will be 1 only. So, what is rise time? It is the time taken by the response of a second order underdamped system to reach 100% of the steady state value. That is 0 to 100% of the steady state value of output. Okay, so this is defined for underdamped system. अगर कोई और सिस्टम होता तो क्या बोलते? अगर मान लो overdamp system है, if it is a overdamp system, then for the overdamp system, the rise time is defined as it is the time taken by the response of overdamp system to reach from 10% to 90% of the steady state value of output. Okay? So for overdamp system, it is the rise time is the time taken by the response of the system to reach from 10% to 90% of the steady state value of output or the final output. But for underdamped system, it is the time taken by the response to reach from 0% to 100% of the steady state value of output. And the formula for rise time is given as TR equal to pi radian minus phi. Phi is what? Angle subtended by the pole location with respect to negative real axis. And the formula for phi, you know, it is either cos inverse zeta or tan inverse under root 1 minus zeta square by zeta. Okay. But remember, the value of the unit of phi needs to be taken in radian, not in degree. Because pi is in radian. So here also, if you calculate phi, it should be in radian. Divided by omega d, which is damped frequency of oscillation, which you can calculate by omega n under root 1 minus zeta square. So this is very important formula. You please note it. So Td was 1 plus 0.7 zeta by omega n. Okay, 1 plus 0.7 zeta by omega n. And Tr is pi minus phi radian by omega d. And how do you calculate this? Although it is not required, you just need to remember the formula, but still I am telling you. I know that Ct was given by the formula, that is my unit step response of a second order underdamped system, because the overall analysis here or the performance specification is seen for second order underdamped system only. So you need not worry about the response. So this response is taken for the second order underdamped system with unit step input. So Ct is 1 minus, it is 1 minus zeta omega n t by under root 1 minus zeta square sine of omega dt plus phi, where phi value is tan inverse under root 1 minus zeta square by zeta. Now, if you place Tr instead of T, so just place Tr instead of T. At that time, the response will become 100% because for an underdamped system, It is the time taken by the response of the system to reach from 0% to 100%. 100% means 1 into 1, because this is my steady state value of output, and 100% means 1. So this part will be 1. So from here you can calculate the value of TR, and the TR will come like this: pi minus phi radian by omega d. Now what is peak time? Peak time is time taken by the response of the system to reach the maximum level of the first overshoot. To reach the maximum level of the first overshoot. Okay, here some queries are there. Ritvik is asking that during drawing the locus of second order system, why we are not considering the roots due to the overdamped case. See, the pole location are in exact harmony in underdamped system and critically damped system. But in the overdamped system, the poles can be anywhere. The poles can be anywhere, and they are equal, they are real, but they are distinct. And we are doing the characteristic of underdamped system. Overdamped system is not accepted in any case because the response becomes sluggish in nature. So while drawing the root locus, I won't consider the pole variation due to the overdamped system, although I have shown it here, but it is not required because I have to connect the locus of the pole to draw a particular shape. If I am going to take the poles due to overdamped system, then what will happen is the root locus will not be symmetrical. And there is a rule of drawing a root locus. Please remember that root locus are symmetrical about x-axis. So when I will consider this part also, it can never be symmetrical, because when I am considering this, I have to consider this also. In that case, root locus won't be symmetrical. So it violates the rules of construction of root locus, and that is the reason I am not considering the pole due to the overdamped case. Okay, only the undamped, underdamped, and the critically damped will be taken into the account because the root locus I am getting is symmetrical. Is that clear, Ritvik? Indrani is telling that sir, slide is not coming. Is that the case? For others also it is the problem. Indrani is telling that slide is not coming. Tell me if the slide is coming or not. Are you able to see the peak time? Yes, Ritvik. Sometime what are you telling? Sometimes slide is coming a little late. Yes, that is the problem with the, because you people are living in different cities. Okay, I belong to a different city, and there is a network problem. And in Google Meet, where I am teaching, there is a lag of I think 15 seconds, 15 or 30 seconds. There is a lag time. Okay, means whatever I will be telling here, what I'll be delivering here, whatever I'll be showing you in the screen, okay, there will be a time lag of 15 to 20 seconds. Okay, this is how the system works. Anyway, the thing is, the concepts need to be cleared. Okay, and if you get any doubt, you can ask me. Okay, so let us start with the peak time. Now, what is peak time, guys? Peak time is the time that is taken by the response to reach the maximum level of the first overshoot. Okay, so I know that whenever See, whenever I am drawing the response of a second order underdamped system due to unit step input, it will be like this, and the amplitude will continuously decrease and finally settle to the steady state. Now what I'm telling is, when you draw like this, the first overshoot will be having maximum amplitude. I already told you that when it start oscillating about the steady state, when our second order system start oscillating about the steady state, this part will be having the maximum oscillation or the maximum amplitude. Okay, and peak is occurring here. So this part, so peak is occurring at this particular time. So this time is actually TP and it is measured from 0. So this part is TP, that is peak time. So it is the time taken by the response of the system to reach to the maximum level of the first overshoot. This is my first overshoot. This is my first undershoot. This is my second overshoot. This is my second undershoot. So the first overshoot maximum level is this. So what is the time taken by the response to reach to the first overshoot? So the response is reaching to the peak of the first overshoot at this particular place. So the time taken is TP. So this is my TP. So TP is represented as n pi by omega d. N pi by omega d, where n represents the overshoot or undershoot. So for any overshoot or any undershoot, if they're asking you what will be the time, okay, what is the time required to reach to the maximum level of the second overshoot, then for second overshoot, I know that n will be equal to 3. Or if they're asking what is the time required to reach the maximum level of first undershoot, so in that case, you will put n equal to 2. But by default, whenever they're asking you the peak time means they're asking you the peak level of the first overshoot. So TP will be represented as n pi by omega d. And for the first overshoot, I know that n is equal to 1. So it will be pi by omega d. But if they're asking for the other cases, that is second undershoot or the first or the third overshoot or the fifth overshoot, okay, then you have to put all these values. For first overshoot, n is equal to 1. For second, n equal to 3. For third, n equal to 5. Now undershoots. For first undershoot, n is equal to 2. For second undershoot, n is equal to 4. For third undershoot, n is equal to 6. So like that it will go. So this is the peak time. And how do you calculate it? See, you know that this was my value of CT. You know that this was my value of CT. Right. Now I know that, and this was zeta omega and t. Now I know that at t equal to TP, the CT value will be maximum, because I know that not only the peak time is the time at which the response will reach to the first overshoot, the response will be at its peak value. The response will be at its peak value. After that, the response will never be able to go to that peak. Okay. So for getting the maximum value of CT, I know that I have to do first order derivative equal to 0. For maxima or minima checking, you do the first order derivative equal to 0. Okay. So you just put this particular part. Okay. Take the first differentiation of this. Perform this first order derivative on CT and equate it to 0 at t equal to TP. At t equal to TP. Put t equal to TP here. Then you will find the value of TP from this and put the value of TP in this particular equation. Okay. You will get the value of CT also. You will get the value of TP also. Okay. Although these derivations are not required, but just for the sake of your knowledge, okay, that how you got all these formulas, I am explaining you the things. So that if you are strong with your mathematical calculation, you can find it then and there. But I would recommend you to learn the formulas or remember the formulas, because it will allow you to solve the problem in a very less time. Okay, because this kind of derivation anyhow it will take time. Even if I will do, it will take time. So that is why I recommend you to remember the formulas, so that you can move on to the next problem after completion of the first problem. Okay, now the next is settling time. Now what is settling time? Settling time is the time taken by the response to settle in a certain range, which is called tolerance band of the steady state value. ठीक है, क्या होता है settling time? If say if I am waiting for the output to get settled, it may take very high time, it may take infinite time also, because I know that my system is oscillating and I don't know how long it is going to oscillate. So in that case, I cannot wait for the response of the system to get settled at a very large time period. So what I do is we consider certain tolerance band or certain range about the output value in which the response of the system after oscillation are assumed to get settled. मतलब say my response, let me draw it here. See, what is happening is, this is my steady state output or the steady state input. Okay, now about this state, okay, about the state, I am considering a tolerance band. So one tolerance band will be like this, another tolerance band will be like this. So I'm considering a range. It may be from, say, if this is 100%, okay, because this is 1, so this is 100% of the output. So what I am doing is, I may consider 98% of the output or 102% of the output equal below the steady state and above the steady state. Equal range I have taken, so that the overall range falls in this. So if I am taking 2%, this is called 2% tolerance band. And if I consider the range of 95% to 105% of the steady state output, then my tolerance band is large. My tolerance band is large. So when tolerance band is large, the accuracy will be less, but the settling time will be, the system would get settled fast. Although here, since the approximation is large, the accuracy is very less. See, if the tolerance band would be large, the accuracy will be very less, but the system will get settled fast. But when I am taking tolerance band very less, then what will happen? The accuracy will be more, but the settling time would also be more. The system would take a quite longer time to get settled. Okay, so since my output response was oscillating, I didn't know when my response will finally get settled. So what I did is I assumed a certain range or a certain tolerance band in which I assumed that my output has already got settled. So in this particular range, say 2% range, I am assuming that my output is settled. So this is called 2% tolerance band. So in within this 2% range, I'm assuming that my output has settled to the steady state value. So if my response while oscillating, say it is like this, so it has fallen in the range, although it is still showing overshoot and undershoot, but it has fallen in the range of this 2% tolerance band. That is why even after oscillation is there, but I am assuming that my output has got settled, because I cannot wait for the control system response to get settled at infinite time. We don't have such a large time, right? Because for the design and analysis, it should be there should be a certain time limit. Okay, so if I'm considering this range to be very less, or a tolerance band to be very less, this will take longer time to get settled. Okay, although the accuracy would be very high. Okay, but when I'm considering this 5% tolerance band, the settling time will be very less. Okay, but the accuracy will be poor. Accuracy will be poor, although the system would get settled fast if I am having higher tolerance band. So if I'm taking 5% tolerance band, my output response will finally get settled, because a lot of oscillation will not be taken into account because it has fallen into this range. So if it has fallen into this range, then it doesn't matter whether it is still showing overshoot and undershoot. It doesn't matter. Okay, so for 2% tolerance band, that is for this particular range, the settling time is 4 by zeta omega n, and 1 by zeta omega n was what? Time constant. I know that my time constant is written as 1 by zeta omega n, right? So for 2% tolerance band, for this 2% tolerance band, my settling time is 4 by zeta omega n, which is also written as 4 times the time constant. So see, when the tolerance band is less, the accuracy is high, but the system would take longer time to get settled. So TS will be more. That means longer time, the response will take longer time to get settled. The response will take longer time to get settled. The response will take longer time to get settled. But since here the accuracy is, since here tolerance band is high, means accuracy will be less. The approximation is high, because the tolerance band is high means what? The approximation that I have taken is high, so accuracy will be less. Accuracy will be less, but the settling time would be low, and lesser settling time is preferred in the control system, because lesser the settling time, faster will be the transient getting died out. Okay, faster the transient will get eliminated from the system, and hence more stable the system will be. Okay, again I am repeating, lesser the settling time is, faster the transient will get eliminated from the system, and more stable the system will be, and the speed of response of the system will also be considered to be fast. Okay, so if settling time is less, means lesser time, the response is taking lesser time to get settled. Okay, and last but not the least, here maximum overshoot. Okay, what is maximum overshoot? Maximum overshoot is the peak value of the response while oscillating about the steady state. I told you that when my system oscillates, like here you can see, when my system oscillates, this is the peak value. This is the peak value. So the peak value is how much? This is considered to be the maximum overshoot. So this part is C at TP, and this part is C of infinity, because this is my steady state output, right? This one is my steady state output at T tending to infinity. So steady state output is written as C of infinity, and this part is C of TP, because this time was what? This time was TP. So the response at this particular time is written as C of TP, and the response here is written as C of infinity. So percentage maximum overshoot is written as C of TP minus C of infinity divided by C of infinity. Okay. So this C of TP minus C of infinity divided by C of infinity will give you the overshoot or the percentage overshoot. So percentage, if you're writing into 100, you have to do. Okay. And here CT max. Okay. If somebody is writing CT max, the maximum value of the response is nothing but 1 plus MP, because this part is MP, the peak overshoot. This part is MP, and this part is 1. This part is 1. So 1 plus MP will give you the maximum value of the response. 1 plus MP will give you the maximum value of the response. Okay. Now, there is a formula for the maximum overshoot. Okay. It is e to the power minus zeta pi. Okay. See, everything is in the numerator. This is x. This overall part is x. And x is nothing but zeta pi by under root 1 minus zeta square. Okay. So the peak overshoot is e to the power minus zeta pi by under root 1 minus zeta square. So you can see that the peak overshoot is the function of zeta. The peak overshoot is nothing but the function of zeta. Function of zeta. It is just the function of zeta. And if you want to calculate the percentage overshoot, you have to multiply this by 100. Okay. Sometime they will ask you what is the peak value of the second overshoot. So if they are asking you the second overshoot, means you have to include a value of n here. So e to the power minus zeta n pi by under root 1 minus zeta square. So for second overshoot, n will be equal to 3. Sometimes they will ask you what is the peak overshoot or the maximum overshoot for the fourth overshoot or second undershoot. For second undershoot, n will be equal to 4. Okay. For second undershoot, n will be equal to 4. So this is how you will find the overshoot. But by default, if they have not mentioned any second overshoot or third undershoot or fourth overshoot, you have to consider the first overshoot only, because the first overshoot will be giving you the peak value of the response. Okay. So the peak value of the response while oscillating about the steady state is your maximum overshoot. And this is my formula that you need to remember. This is the formula that you need to remember. Is that clear? So if zeta will change, maximum overshoot will change, because maximum overshoot is nothing but the function of zeta. So if zeta is going to increase, definitely maximum overshoot is going to decrease. And if zeta will decrease, maximum overshoot will increase. Okay, now I'll show you the overall specification parameter with the response. So this was my response of a what response? An unit step response of a second order underdamped system. So I have just magnified the overall response so that you can understand everything. So what was delay time? What was delay time? Delay time was the time taken by the response of the system to reach 50% of the steady state value of the output at its first attempt. What was TR? TR was rise time. What is rise time? Rise time is the time taken by the response of a second order underdamped system to reach from 0 to 100% of the steady state value of output. Okay, so this is rise time. What was peak time? What was peak time? Peak time was the time taken by the response to reach to the maximum level of the first overshoot. Okay, because the first overshoot only will give you the maximum value of the response. So it is the time taken by the response, this is my response, to reach to the maximum level of the first overshoot or the peak value of the first overshoot. So as you can see, this is my first overshoot, second overshoot, third overshoot, first overshoot, first undershoot, second overshoot, second undershoot, third overshoot, third undershoot, like this. Okay, and finally my system is going to get settled, but I don't know when it will get settled. So I have drawn a tolerance band. So this blue line is showing you the tolerance band. So this is the range or the tolerance band that I have assumed, in which I consider that if the response falls into this range, then I will consider that my system has got settled. So this is my settling time. This part is my settling time. So you can see that the settling time is greater than, because the settling time is huge. Settling time is greater than the peak time, is greater than rise time, is greater than the delay time. Delay time formula was 1 plus 0.7 zeta by omega n. The rise time formula was pi minus phi by omega d. Peak time formula was n pi by omega d. Settling time formula was for 2% tolerance band, it was 4 by zeta omega n, and for 5% tolerance band, it was 3 by zeta omega n. Acha, this was my peak overshoot or the maximum overshoot, and the formula for maximum overshoot was C of Tp minus C of infinity divided by C of infinity. Otherwise, you have to remember the formula MP is equal to e to the power minus zeta n pi by under root 1 minus zeta square. So this will all be at the numerator, above the exponential part. Okay, so this, if you want to calculate percentage overshoot, multiply by 100. So e to the power minus zeta n pi by 1 under root 1 minus zeta square. ठीक है, ये पार्ट एक साथ रहेगा, ध्यान रहे। ऊपर में ये मान लो e to the power minus x है, तो ये हो गया आपका x। ठीक है, so all the formula is written here to summarize you everything. ठीक है, what is the maximum value of the response? It is 1, because this part is 1 and this part is MP. So 1 plus MP is the maximum value of the response. This is delay time, this is rise time, this phi should be in radian, remember that, and settling time is 4 by zeta omega n for 2% tolerance band, and it should be 3 by zeta omega n for 5% tolerance band. Okay, so I hope everything is clear to you. Tell me, everyone, Indrani, Ritvik, Srijita and whoever are there, please inform me if there is any doubt or if you understood everything or not. Tell me if the class was exciting or not. So here we complete our second order system also. So time response analysis has been completed. Now two topics are left, which I'll cover it tomorrow in the first 15 to 20-minute session, and then we'll start with the numericals. Okay, numericals on the first transient response of first order system and transient response of second order system. So for the first 1 hour, what we are going to do tomorrow is, first we'll study about dominant pole concept and what is the difference between steady state error and actuating error, that we are going to cover, and then certain numerical on the transient response analysis we are going to see. Okay, and after that we'll solve some numericals, and then what we'll do, we'll start with the next unit, that is called the stability, where we'll be using Routh-Hurwitz criteria. Okay, so till then, be safe guys and keep practicing, keep revising. Okay, and see you tomorrow. Thank you all.